In this video, we'll use R to demonstrate how to set up a whole line confidence interval. Note, this will not be the working hoteling interval required for your homework, but hopefully this will give you an idea on how you could go about setting that up. We'll also discuss how we implement a general linear f-test and calculate ANOVA tables in R. So I'm going to be using the cars dataset and looking at the speed and distance. This is how fast a car is going and then the distance it takes the car to stop. Instead of doing cars $speed and car $distance throughout the whole process, I'm just going to use X and Y to save myself some typing. So this is going to have 50 observations, and I'm going to use alpha just to be my overall indication of my alpha level of 0.05 so that I can just type in the variable alpha instead of having to type in 0.05 over. So I'm going to fit the model. The intercept is -17. The x slope is about 4. So as x increases, as the speed increases by 1, the distance increases by about 4, give or take. Now the goal is to create the confidence interval and then to plot it. So I'm going to need the MSE to create the confidence interval. Note that I can get the MSE from a fit model by taking sigma of the model and then doing sigma of the model squared. So sigma of the model is the square root of the MSE. If I square it, then that gives me the MSE. And then I'll use x bar. It's just the mean of x. Now, as we talked about, I'm going to want to plot all of the different x values in a range of x's. So the range of x's that I have in this particular case is from 4 to 25. So I'm going to create a sequence from 4 to 25, and I'm going to go by 0.01. Again, this is going to be my infinite number of x's. It's not really infinite. There's just going to be a whole ton of them, like 21,000 of them, or 2,000 of them, 2,100 of them, or 200 of them. So this is just going to be a whole ton of different x values that I'm going to use for plotting, and I'm going to call it px for plotting x. Now I'm also going to do py hat. This is going to be my plotting y hats. Now this, if you remember right, when we calculate the interval, the y hat is the center of the interval. We have y hat plus or minus, and we have that critical value times the standard error. So I'm going to need all of those y hats for each one of those x values. Now this is where you're going to get the confidence interval versus working hoteling. This is not working hoteling. But for the confidence interval, I use a t critical value. So this is my t critical value. I use the alpha over 2. I've got degrees of freedom is n-2. So this is the t critical value for a confidence interval for the mean, not the working hoteling. Now the margin of error, if you think about the confidence interval equation, you've got the point estimate plus or minus the critical value times the standard error. The margin of error is that second piece after the plus or minus in a confidence interval. So this is the critical value times the standard error. So I'm just going to make a margin of error. Now note that the standard error, I've got px, the plotting x's, minus x bar. So this is all, I could also have called this x sub h. This is all of my different x sub h values. Note that I've got the sum of squares x, so this doesn't involve x sub h at all. This is that fixed quantity, sum of squares of x in the denominator. In fact, it may have been easier to write sum of squares of x as its own calculation, x minus x bar, quantity squared, and then adding all those up, and then just wrote sum of squares of x down here. That's not what I did, but you could do that. So I'm going to calculate the margin of error. Note that this is a different margin of error depending on each x value. And recall, if you will, that the confidence intervals curve in and out. It curves on the in when it gets close to the mean, and it curves out as it gets towards the edges. So we're expecting this to be a different margin of error for every value. Now I'm going to get the low part of the t confidence interval by taking the So if you remember right, the confidence interval is plus or minus. The low part is the minus part. The high part is the plus part. So I'm just splitting that into two different components and labeling that as the plotting lows and then the plotting highs that I'm going to take advantage of in a second. So I've got the plot of x and y. Now if I want to plot the line of best fit, I could just make a line for all of the px's and the py hats. So these are the plotting x's and then the predicted y hats for each of those plots. So I can add that onto this graph. Then I can add the low value, the low confidence interval value, and then the upper confidence interval value. And again, you see it kind of curves in the middle. This is expected, as when you're in the middle, you have a lower range of error. Where you're on the edges, you have a higher range of error. And that should intuitively make sense. And based on the equations we discussed in the last lecture, that should make sense as well. So this is how we'd go about this. Again, you'll have to modify this to make the working hoteling band work. But I would tend to do this with a separate set of plotting characters such that this line is really high resolution so that we get this nice smooth curve. Now with this many data points, you would probably get, you'd probably get a decently smooth curve anyway. Sometimes you will, sometimes you won't. Depends on how many data points you have and if they truly are continuous over the x-axis or not. All right, so for the ANOVA, I'm just going to pull in the BSDA just for a data set. We'll use the undergrad data set. Looking at the top of the undergrad data set to make sure it read in appropriately, we have gender of students, their major, their class, the GPA, the SAT, and then the number of dropped classes that they have. And so our goal is going to see, does the SAT predict the GPA of freshmen? So you take the SAT when you're coming into class, does that actually do anything to predict your GPA? So we can look at the summary of the model, and we can look and do our traditional interpretations. Again, we could do our interpretations with the intercept and the SAT, but we remember first we check statistical significance before we move on to those interpretations. Then we can look at doing, and this is what we would normally do for our model from what we talked about thus far. So this is our summary. However, what we talked about was doing the ANOVA table, where we break up the significance components due to the model and then the significance components due to the errors or the residuals. So if we do AOV, that stands for analysis of variance in R, this does kind of give it gives us sums of squares and degrees of freedom. We talked about that those are things that we look for, but the format is super weird. What's a more familiar format is if we do summary of the analysis of variance of the model. This gives us the more traditional format where we've got the model, and again, the different components of the model, the degrees of freedom, the sums of squares, the mean squares, the F value, and the P value. Note that the P value is going to match exactly with the P value of the slope when we break it out by individual components in simple linear regression. With multiple linear regression, when we start adding in other variables, this may or may not match depending on how you're doing your calculations. All right, so for the general linear test, we fit a full and reduced model. I'm calling them mod sub F for the full and mod sub R for the reduced. The full model is going to have SAT predicting the freshman year GPA. The reduced model is just going to have one predicting the freshman year of GPA. And if you remember in class, we talked about how you've always got the Y bar. You've always got the mean of the Y values that can be your predictor. That's what this model is fitting. The one is fitting the intercept only model. So that's the mod R for the reduced model. Now to run the general linear test, we use the ANOVA command, and we feed in the reduced model first and then the full model second, or the bigger model second. In doing the ANOVA command, comparing the reduced model to the full model, we see the change in degrees of freedom. We see the change in the residual sums of squares. And then we see the calculated statistic according to what we saw in class in terms of the F statistic and the p-value. And we see that this p-value matches identically to the degree of rounding with the previous p-values that we found when we looked at the test of the slope, when we looked at the ANOVA test, and now when we're looking at the general linear F test. All of these match perfectly. Reading this ANOVA table, we read down, we see that Model 1 and Model 2 are being compared, and here's a summary of those two models. We see that Model 2 is statistically significantly explaining more error than Model 1. And what this would indicate is we by default go with the smaller model, Model 1, but because Model 2 works statistically significantly better than Model 1, we decide to go with Model 2, or the model with more variables in it. This has been a video demonstrating how we construct a continuous interval for a confidence interval of a data set, how we construct an ANOVA table for regression, and how we perform a general linear F test using R.